So this is screencast 2 of chapter 3, and in this screencast we'll look at ecosystem productivity. Some ecosystems are high in productivity and some are relatively low in productivity. So first, some vocabulary terms. First is gross primary productivity. Okay, so that means the total amount of solar energy that the producers in an ecosystem capture via photosynthesis over a given amount of time. So it's primary productivity because we're talking about producers. Gross means total. It doesn't mean icky. So it's just as in economics. Gross primary productivity, the total amount of solar energy that is captured by producers via photosynthesis. And the second term is net primary productivity. So that is the energy, total energy captured minus the energy respired by the producers. So remember we have, for example, a plant. And remember I said it's not just the mouse or animals that are respiring. Plants also use some of the energy that they've captured through photosynthesis for their own life, to grow, to reproduce, even to move, bend toward light, for example. So that energy that remains that can be passed to the next level, let's say the something eating the plant, that's its net primary productivity. Now, this graph shows you the comparison of the primary productivity of different ecosystems. First we have continental ecosystems, and on the bottom we have marine ecosystems. So you can see, you probably would have guessed tropical rainforests are up high on the primary productivity, but so is, net primary productivity, but so are swamps and marshes. So swamps and marshes are ecosystems that are partially or completely submerged in water during most of the year, and they are the highest productive areas of all continental ecosystems, and actually of all ecosystems in general. So even though we may not feel a natural, well, let's see, not natural attraction, but even though we might not feel that it is as productive as a tropical rainforest, it's very important to us, and that includes here on Cape Cod. Moving down the line, we have tropical seasonal forest, which means a warm seasonal forest. The type of, next one here is temperate rainforest, which would be like in Washington State and Oregon. And temperate seasonal forest, which is what we have here on the East Coast in Massachusetts. Temperate, we have rather moderate temperatures, not hot, not freezing cold. And our forests are seasonal. In other words, our deciduous trees lose their leaves in the winter. Then we're moving down here to boreal forests. Those are cold weather forests, for example, in Canada, west coast of Canada. Savannas or plains. And then surprisingly down here, we have cultivated land. That's pretty low on the productivity. And you might think cultivated land, in other words, agricultural land, would be very high in productivity, but it's not. And moving down, we have temperate grasslands, tundra, cold, treeless climates, all the way down to deserts. Now, looking at marine ecosystems, you might have guessed this one, but coral reefs are, of course, at the top here, followed by salt marshes. So very similar to the freshwater, but in this case salt, very high in productivity. Upwelling zones are zones particularly off of the west coast of continents where the ocean pulls away from the coastline and deeper waters are brought to the surface, and that brings up a lot of nutrients that had gone down and drifted down through gravity, and brings a lot of nutrients, which then makes it very productive, relatively speaking. Next up is the continental shelf, or the area just off the coastline where, for example, we do a lot of fishing. And then you have the open ocean. On the right here, we're looking at how much energy comes from the sun and how much of it is actually able to be captured. So you can see that 99% of solar energy passes through ecosystems or is reflected by the surface of the earth or cloud cover without even being absorbed by anything. And only 1% then strikes the producer and is able to be captured by photosynthesis. And then of that gross primary productivity, 60% is lost to respiration, so only 40% becomes the net primary productivity. So 40% of 1% is a very small amount of net primary productivity versus what originates with the sun. Okay, now this is a very important concept to grasp here in environmental science. So let's take a minute to look at it. First, we are looking at energy transfer efficiency, which results in a trophic pyramid. So we have on the base here producers, those which are capturing the energy from the sun, and that amount of energy here, represented here with 10,000 joules. That's just an example, okay? Joules is a unit of energy, and it's saying that if we start with 10,000 units of energy at the producer level, only 10% of that, in other words, 1,000 joules, is obtained when the primary consumer consumes the producer. And yet again, moving up the next trophic level, only 10% of the net energy here is transferred and available for use by the secondary consumer. This is why it's more rare to get to a tertiary consumer on land, because we would be getting down to only 10 joules at the next level and so forth. So the more consumer levels that the energy flows through, the less energy is obtained. So that's referred to as ecological efficiency, the proportion of consumed energy that can be passed from one trophic level to another. Actual efficiencies in nature range from, depending on who you quote, between 5% and 20%. But actually 10% is the most common and certainly the average efficiency. All right, so you may want to grab a pencil and paper for a moment as I want to give you another example and make sure you understand the what would happen with the energy as we go through various trophic levels. So let's start with some flowers. And let's say those flowers have 20,000 joules worth of energy. And butterflies dine on those flowers, or the nectar of those flowers. So the butterflies would then be able to obtain 2,000 joules worth of energy. So only 10% of the energy that was existing in the flowers would be transferred to the butterflies. So what if we then went up another level to birds that eat the butterflies? How much energy would be transferred to birds? Well, if it was 20,000 at the producer level and 2,000 joules at the butterfly level, the primary consumer level, then it would be 200 joules at the bird level or the secondary consumer level. And if something ate the bird, then that would be down to 20 joules of energy. So it's always going to be a loss, and you would never gain more energy through these systems. So you would never have a higher number as you go through each feeding level. And the relevance of this for humans is if we want to feed an ever-growing population, the more that we dine as a primary consumer, the more energy or food energy can be available to that growing population. And that's something that we will revisit again. But the more we rely on meat, the more area of land it takes, but also the less energy that is transferred to us because, in terms of efficiency, because it takes so much for that cow to grow and so forth. Okay, I will end this one at this point and move on to the third screencast.